Dear students, the topic of this lecture is Maxwell's equations. We have discussed about Maxwell's equations in our earlier lectures, and we observed that these equations are of very much importance in the case of electromagnetic theory or electromagnetic wave propagation. And in this lecture, we will start with the static field equations, and we will modify these static field equations in order to account for the variable time. That is what happens to these equations when the time variable also is coming into picture, that is the electrodynamic conditions. And the static equations the modified form of the static equations are actually called Maxwell's equations. So we are quite familiar with this static field equations, that is the four equations. The first one is Gauss law, that is del dot D is equal to rho by epsilon 0, or surface integral E dot ds is equal to 1 by epsilon 0 volume integral rho dv. Then the second equation gives the conservative nature of electrostatic field given by the differential form del cross E is equal to 0, or closed line integral E dot dl is equal to 0. Then the third one is the Gauss's law for magnetism, or it is a non-existence of magnetic monopole. That is del dot B is equal to 0, or surface integral B dot ds is equal to 0. And the last equation is Ampere's law or Ampere's circuital theorem, and its differential form is del cross B is equal to mu 0 j, or closed line integral B dot dl is equal to mu 0 into surface integral j dot ds. So these four equations are the fundamental equations of electrostatics and magnetostatics. And we will modify these equations in order to include the effect of time variable also. So before Maxwell, the modification is given to the conservative nature of the electrostatic field equation only, that is del cross E is equal to 0, and that is given by Faraday. And Faraday's equation, we have studied about Faraday's law, that is del cross E is equal to minus dou B by dou T, that is the time variable is coming into the equation, and that is a modified equation. And before Maxwell, scientists thought that this is the only modification needed to explain all electrodynamic phenomena. So electrodynamics before Maxwell, the equations, the four equations used before Maxwell are listed here like this. The Gauss's law, there is no change for the Gauss's law. The only change is happening to the conservative nature of electrostatic field, that is del cross E, right now changes to minus dou B by dou T. And correspondingly, the integral equation also changes. Line integral E dot dl is equal to minus surface integral dou B by dou T dot ds. And there is no change for the other two equations also, that is Gauss's law in magnetism, del dot B is equal to 0, and the Ampere's law, del cross B is equal to mu 0 j. So these four equations are assumed to be correct or sufficient to explain all the electrodynamic phenomena during the initial days, that is before Maxwell. But Maxwell observed that these equations are not consistent to time varying conditions. So it is not possible to explain all electromagnetic phenomena by only giving the time varying factor to the del cross E equation, that is del cross E is equal to minus dou B by dou T. That term only is not sufficient to explain all electrodynamic phenomena. So he verified this concept by considering the Ampere's circuital theorem, and he showed that this is not consistent for time varying situations. Now taking the divergence of this equation, del dot del cross B is equal to mu 0 del dot J. Now we know that the left hand side is equal to 0 because del dot del cross B is equal to 0. So this equation changes to del dot J is equal to 0. And the del dot J is equal to 0 means this equation is the equation of continuity for steady state. Del dot J equals 0 is the equation of continuity for steady state. So he concluded that the Ampere's equation del cross B is equal to mu 0 J is not consistent with the time varying conditions or time varying currents. So that gives only the equation of continuity for steady currents, or it is only suitable for steady state conditions. So that holds only for steady currents. So Maxwell modified Ampere's equation by adding one more current term, and that is called the displacement current term. So we have discussed about the displacement current term in our earlier lecture. So he added that term JD also with the already existing current term J, that is J is nothing but the conduction current term JC. So del cross B is equal to mu 0 J plus JD. Now taking divergence, as in the previous case, taking divergence on both sides, then del cross B is equal to mu 0 del dot J plus JD. As usual, left hand side is equal to 0. So in this case, we get del dot J is equal to minus del dot JD. Del dot J is equal to minus del dot JD. Now for time varying conditions, for time varying currents, we have the equation of continuity as del dot J is equal to minus dou rho by dou T. Okay, so this is the equation of continuity for time varying currents. So we are substituting that value in this equation for del dot JD. So we get del dot JD is equal to dou rho by dou T. Del dot JD is equal to dou rho by dou T, or it is equal to dou by dou T of del dot D. Now rho is equal to del dot T, that is Gauss Flux Theorem. So rho is equal to del dot T, that is substituted, or it is equal to del dot dou D by dou T. Or removing this del from both sides, we get it as JD is equal to dou D by dou T. So this is the equation of the displacement current that we have already derived in our previous lecture. So the modified form of Ampere's circuital theorem is del cross B is equal to mu 0 into J plus dou D by dou T. Or in terms of electric vector E, this may be represented as del cross B is equal to mu 0 J plus mu 0 epsilon 0 dou E by dou T. So D is substituted as epsilon 0 E. So mu 0 epsilon 0 dou E by dou T. So this is the modified equation, or this Ampere's modified equation, and it is called Ampere Maxwell equation. In some certain situations it is called Ampere Maxwell equation. So this equation, we can see that it is consistent. It is consistent with the time varying conditions also. So these four equations, that is by giving additional correction to the Ampere equation, that is Ampere Maxwell law, also included into the set of equations, and we get the four Maxwell's equations. The first one is Gauss's law, the second one Faraday's law, third one Gauss's law for magnetism, no change for these three equations, and last one Ampere Maxwell law, that is del cross B is equal to mu 0 J plus mu 0 epsilon 0 dou E by dou T. And the only contribution given to this equation by Maxwell is that of the displacement current term dou D by dou T. But these four equations are generally known as Maxwell's equations. And we can see that these four equations are the basics of entire electrodynamics. All electrodynamic phenomena can be explained starting from these four equations. So in all applications such as the electromagnetic communication scenario, or in the case of all industrial, scientific and medical applications or research applications of electromagnetism, we have to start with, or it is able to start with, these four equations. Now what happens to these equations if there are they are analyzed for a source-free region, that is for free space region, and where we are assuming that there is no sources present. And in that case, rho vanishes rho, the charge density rho and current density J tends to 0. So this equation may be modified like this: del dot E is equal to 0, del cross E is equal to minus dou B by dou T, del dot B is equal to 0, del cross B is equal to mu 0 dou D by dou T. That is the current terms. Mu 0 J is removed from Ampere's law, and rho by epsilon 0 is removed from Gauss's law. So these are the equations, Maxwell's equations for a source-free region, and these are called source-free Maxwell's equations. Now let us consider the derivation of these Maxwell's equations. Now the derivation of these Maxwell's equations is, we have already derived these equations in our earlier lectures here and there. So I would like to just compare those things that we have explained or discussed in our earlier lectures. So first let us consider the equation, the first equation, that is del dot B is equal to 0, or non-existence of magnetic monopole. Non-existence of magnetic monopole represented by surface integral B dot ds is equal to 0. Surface integral B dot ds is equal to 0. Now, in order to verify this result, just consider a bar magnet with the north and south represented here like this. And we know that flux line starts from the north pole and end up the south pole through the outside region. And we can also see that the field lines moves from the south to north through the inside region of the bar magnet. Now, if we consider any closed surface, a closed surface is shown here. For this closed surface, we can see that the total normal component of B dot ds over this closed surface is equal to 0, because the number of flux lines emerging out is equal to the number that entering in. Okay, at this region flux lines are coming out, but we can see that corresponding to this region flux lines are entering. So that for the considered surface, the total flux lines coming out is equal to that entering, so that the total total tends to 0. Now, this is also correct for any type of surface. So in this case, we have considered another surface, a small surface that includes only the north pole, like this, only the north pole. But here also we can see that the number of flux lines coming out here, but flux lines are entering here like this through the surface. So if you take the total surface integral of B dot ds, surface integral B dot ds, here also it becomes 0. And this is correct for a solenoid case also. In the case of solenoid also, we are able to consider surfaces like this, and we will get the result, surface integral P dot ds. Even a single current loop is taken. Now in this case, we have a solenoid of length L, but here only one turn is considered, only one turn. And even for a single turn, we can see that one side becomes a north pole and the other becomes a south pole, depending upon the direction of the current. So it is not possible to separate a north pole or a south pole separately. Not possible to separately consider north pole or south pole, and that is the non-existence of magnetic monopole. So the differential and integral forms may be written like this: surface integral B dot ds is equal to 0, and when converting that into volume integral, that is surface integral B dot ds is equal to volume integral del dot B dV, and that is equal to del dot B is equal to 0. So this much, or this argument or this logical explanation is sufficient for the proof of del dot B is equal to 0. Now for the second case, that is Gauss flux theorem. So we have discussed this in our earlier lecture, and the link related to that is given. Also this lecture is in the lecture series related to electrostatics. There we have a topic, Gauss flux theorem, a lecture related to that, Gauss flux theorem, and there the proof of this is given, and a few slides related to the derivation part also is shown in this picture. So it shows that surface integral E dot ds is equal to q by epsilon 0, or the general form is surface integral E dot ds is equal to 1 by epsilon 0 volume integral rho dv, and that is the integral form of Gauss flux theorem. And the differential form also is given, that also is available in the same YouTube video. And we observe this result like this: del dot E is equal to rho divided by epsilon 0. So coming to the next one, that is Faraday's law. That also is already discussed under the title Faraday's law with this particular link, and the corresponding slide is, the picture of that slide is shown, and there we got this integral form as line integral E dot dl is equal to minus surface integral dou b by dou t dot ds, and the differential form is obtained as del cross C is equal to minus dou b by dou t. Then the next one is the Ampere-Maxwell equation, that is closed line integral b dot dl is equal to mu 0 surface integral j dot ds. So we have discussed this right now in the initial part of this lecture itself. So we have to take this or make the proof of this equation by simply considering a straight line current, and suppose at a distance s, from this current, the magnetic field is given by B is equal to mu 0 I by 2 pi s, or closed line integral B dot dl is equal to, when we put this value here, mu 0 I by 2 pi s into dl, or mu 0 I by 2 pi s into line integral dl. Line integral is equal to 2 pi s, so it is equal to mu 0 I. So this is a simple proof of this Ampere's law for a straight current by taking the equation of the flux at a particular distance s as mu 0 I by 2 pi s. So it is a simple proof. We have other fundamental proofs also, that is by making use of Biot-Savart law. We were able to derive this expression for B, and it's possible to substitute here. Okay, anyway, starting from this equation, it is sufficient to start from this equation. Then check the inconsistency as we have explained in the initial slides of this lecture, and a part is given here, and we get this equation as del cross B is equal to mu 0 into j plus dou d by dou t. Its integral form also is given. So this is sufficient as the proof for the last equation. So during this lecture, we started with the static field equations, then applied required modifications in order to incorporate the time effects. The first one is Faraday's law, and then the next modification is for Ampere's recurrential theorem, that is given by Maxwell, and the modified equations are called the Ampere-Maxwell equation, and the four equations together are known as Maxwell's equations. Then we also considered equations for source-free region, and the last section, the derivation, the required points needed to derive for these equations are also discussed in this lecture. Okay, thank you for watching.